Hi, good afternoon everyone. This is Susheel and I'm here to discuss our work on building a hybrid model for learning embeddings and logical rules from knowledge graphs. This is joint work with my advisor, Professor Jennifer Neville. So what are knowledge graphs? Knowledge graphs hold large banks of relational data about the facts of the world. So the nodes represent concrete or abstract entities and the edges between them symbolize relationships or predicates. So it is often useful to think about knowledge graphs as a set of triplets of the form HRT, which stands for head, relation, and tail. So for example, here we have Lionel Messi as the head, plays sport as a relation, and football as tail. The predicates in a knowledge graph subscribe to a variety of patterns like symmetry, reflexivity, transitivity, and compositionality. And symbolic logical rules can easily capture these patterns. So for example, we have the teammates relationship on the right, which shows reflexive nature, and we can easily capture it as a rule which says V1 being teammates with V2 implies V2 being teammates with V1. So we can also capture the play-sport relationship, which is compositional in nature, very succinctly. The knowledge graph completion problem or link prediction amounts to inferring new knowledge based on existing ones in the knowledge graph. So, for example, here we have Ronaldo playing for Juventus and Juventus being a football club. So, from the compositional nature, we can infer that Ronaldo plays football. So traditionally, mining or rule learning takes inspiration from inductive logic programming, and multiple methods have been proposed in the literature, and they fall into two different paradigms. The one is a top-down approach where we start from a general rule and try to get as specific as possible by clause exploration, and the other one is a bottom-up approach which starts from a very specific rule and tries to get as general as possible so that it fits the data better. As one can imagine, both of these amount to a search problem in a very vast search space of all possible rules. And much of the efforts in the community have been in developing pruning strategies so that we can make this computationally efficient to learn. So, another point is that using logical rules helps us in generalizing to data which is very sparse, and it also yields good explanations for the predictions it makes. So this is especially useful for explainable AI. So another competing approach to knowledge graph reasoning is that of knowledge graph embeddings, where the idea here is to learn how to represent entities and relations as points in vector space. And hopefully this vector space can capture the inherent structure of the knowledge graph, something akin to word to vec. Because the entities and relations are stored as continuous vector representations, we can easily model the triplets using a score function. So the score function essentially estimates the likelihood of the triplet being true. A higher score means the triplet is more plausible. Because the score function is parameterized with learnable embeddings, the learning process is now to maximize the score for the correct triplets while minimizing the score for the incorrect ones. Because there are no negatives which are available in the knowledge graph, we have to resort to negative sampling where we randomly perturb existing triplets to form a negative set, and this set along with the loss function is optimized using gradient descent. And hopefully we can backpropagate our losses back to the entity and relation embeddings and learn them from data. Multiple methods have been proposed in the literature, and Transy being one of the earliest and the most simplest ones. So in Transy, the score function is just a translation in Euclidean space. So how do we actually perform reasoning or link prediction given such a score function? Let's say we have an input query which asks for which club Buffon plays for. What we can then do is generate a set of all possible triplets with the query at hand and ask the score function to score each one of them. And hopefully the one which gets the highest score is our target. So here Juventus is the answer. I have to point out that it's computationally efficient to learn these embeddings and inference is quite fast. And another advantage of embeddings is that it can learn these global statistical patterns which are available in the knowledge graph. Some of the drawbacks of embedding methods is that embedding representations are quite poor for sparse entities. This is essentially because representation learning is as good as the quality of the training data. Another drawback is that it's difficult for vector representations to learn complex local compositional patterns. As one can imagine, both of these drawbacks can be easily be solved with the help of logical rules because they can generalize to sparse entities and they can also learn these kind of compositional patterns. So this motivates us to ask the research question on how we can use the generalizing ability of logical rules to make these embeddings better. So it's not all a rosy picture with logical rules. They are quite brittle in nature, and low quality rules are mined especially when the data is noisy or incomplete. So below I have a rule which states that a player V2 is called the greatest of all time if he is essentially teammates with another player V1 who happens to be a greatest of all time player. Now, although this rule has multiple instantiations on the knowledge graph on the right, for example, Buffon and Ronaldo both subscribe to this rule. Similarly, Messi and Iniesta do so. But it will also predict that Dembele, who is still an upcoming young player at Barcelona, is the greatest of all time, essentially because he is teammates with Messi. So, how do we prune out such noisy or absurd rules? We could do that if we had a pruning strategy which could look at the global statistical patterns in the knowledge graph. So specifically in this example, if we had an embedding method which could model the correlation between the player being called GOAT and the high number of sporting awards, we can easily prune out such a bad rule. So here I have an example of Rescal which models Ronaldo and players like him with a high score and Dembele with a low score. Embedding methods are also robust to noise as triplets are modeled probabilistically. So this motivates us to pose a research question on how we can use the feedback of the embedding models to improve the quality of the mined rules. So motivated by the two research questions which were posed earlier, we develop our framework which uses the complementary properties of both embedding methods and rule mining so that they reinforce each other. So, on a broader level, given an input knowledge graph G-train, we initially learn a set of entity and relation embeddings called theta I. We use theta I to prune the search space of the rule mining phase. And once we have a set of rules tau, we get the groundings of these rules and sample them to augment it back to the initial knowledge graph. An embedding method is now learnt on this augmented knowledge graph, and this iterative process happens for a number of rounds. And hopefully, at the end of this process, we are left with embeddings which are structured from the rule mining phase, and we have high quality rules which have been guided by the embedding method. So, let us see how the embedding learning actually happens. So in embedding learning, initially we are given a set of triplets GI plus and the superscript plus indicates that we only have positive samples. We associate a label YHRT for each triplet and for all the positive samples we label YHRT as 1. So the main assumption in embedding learning is that the labels are conditionally independent given their latent representations or embeddings. This allows us to write the probability distribution of the set of labels capital Y as a simple product of Bernoulli distributions of the individual labels. So because the score function is parameterized with theta, which happens to be our entity and relation embeddings, the goal of the optimization process is to measure the criteria of the saliency of the triplets and try to minimize the loss. So because we don't have negative samples, we generate these negative samples from GI plus as I mentioned earlier, and we calculate the loss over this extended set of both positives and negatives. So given that we have learned some intermediate representations for the entities and relationships as theta I from the previous step, we will see how we can prune the search space of the rule mining algorithm using theta I. So firstly, let's see how we can perform top-down clause exploration, going from a general to a more specific rule with the help of three mining operators. So initially, let's say we have the place port relation which states that V1 placed this port V2 as our head atom. We can extend this by first adding a dangling atom wherein one of the arguments is shared with the original rule and the other one is a fresh variable. So here V3 is the fresh variable and V1 is shared with the original rule. We can also add an instantiated atom wherein one of the arguments is a constant in our universe and the other one is shared with the rule. And finally, we can also add a closing atom wherein both the arguments are shared with the rule. So here V3 and V2 are both shared with the original rule. This is essentially done to keep a tab on the search space so that we only mine safe and closed rules. As one can imagine, the search space is huge and we need an effective pruning strategy to filter out low quality roles. And this is essentially done with the help of standard confidence. So, standard confidence is a notion of measuring the number of predictions that the rule makes which are actually present in the knowledge graph. So, the higher the standard confidence means that the quality of the rule is higher. So, as one can imagine, standard confidence is based only on the available training knowledge graph and it doesn't model the triplets probabilistically. So, let's see how we can improve this pruning strategy by making use of the embedding methods. So, to do this, we first start with the groundings of a candidate role tau for whom we have to measure the quality factor. We define S tau, which is a set of all groundings of this candidate role. So essentially this means the set of all head atoms that it predicts from its valid body atoms. We measure the quality of this S tau with the average embedding score as a measure to quantify how well tau generates triplets outside the known knowledge graph. The reasoning behind this is that we want to explore candidate rules which explain facts beyond the known kg, and hopefully our embedding confidence measure quantifies this. We then weight both the standard confidence and embedding confidence to form a heuristic pruning strategy or the Q factor for a candidate tau. Here, omega is the weighting factor, which is a hyperparameter which can be tuned later on. If there is an increase in Q, we continue the exploration, else we filter this candidate rule out. We also use additional language biases like limiting the length of the rules to keep a tab on the search space. So now that we have the mind rules which have been guided by the embedding method, we are ready to augment the newly inferred facts back into the original knowledge graph so that the embedding method can use this structure. So instead of naively augmenting these newly inferred facts, we use an importance sampling method which samples based on the embedding score we assign in the previous step. Then we continue embedding learning on this extended set of triplets and the iterative process is run for a number of rounds. So in order to quantitatively measure the performance of our method, we compare ourselves to other standalone embedding methods and hybrid baselines on three benchmark datasets, Freebase 15K237, which is a knowledge graph based on a variety of topics in Freebase, the WordNet 18RR, which is a knowledge graph based on English words, and Yago 310, which contains facts about people and other things. We consider the standard task of link prediction, where given an input query, we are tasked with predicting the missing entity, as shown in this Eiffel Tower and Paris example. So for a set of test triplets, we generate a set of entities by replacing one of the entities with all the available entities in the knowledge graph and score each one of them. And the rank of the correct entity H, for example, is the head rank. And similarly, we replace the tail with every other entity and calculate the tail rank. The mean reciprocal of these ranks is the MRR and the hits at which they occur is the hits at k. So we calculate based on hits at 1, hits at 3 and hits at 10. In all the cases, the higher the numbers mean the better the method is. As you can see, our method beats the existing standalone methods and the hybrid baselines across Freebase 15K237 and Yago 310, and it's almost comparable for the WordNet 18K RR dataset. So we now experiment to evaluate the quality of the mind rules based on a notion of precision. So precision measures the ability of the set of mind rules to infer facts beyond the trained set. The idea here is that the higher the overlap is of the set of inferred facts G tau is with the test set G test, the higher the quality of the mind rules. The below table shows AMI plus, which uses standard confidence, and our method which uses embedding confidence for the pruning mechanism. Across both data sets, we can see that the precision is increased. We now evaluate our hybrid model with respect to sparse entities, especially in the test set. So we define sparsity based on the frequency in which these entities occur, and sparsity is a number between 0 and 1. So the higher the sparsity, the sparser the entity is in the data set. So on the right, we have two data sets on which we evaluate this. One is Freebase 15K and the other one is WordNet 18RR. In both of these data sets, we only have entities which have a sparsity of 0.995. and in the hatched bar plot is our method. And as you can see, our methods beat standalone methods and hybrid models on HitSet 10. These results show that rules do help in structuring the embedding space, and the representations of the sparse entities have improved. Next, we also perform an ablation study with different score functions. In the plot below, the hatched line represents our framework, and across both the data sets and for two different metrics, HitSet 10 and MRR, and across all the different scoring functions, transy, complex, and rotatee, our method performs well. This shows that the data augmentation procedure is useful for any embedding method. So in conclusion, we have developed a hybrid method which utilizes the complementary properties of both logical rules and vector representations. We have experimentally showed that rich data augmentation, guided by the rule mining approach, helps in learning superior embedding representations, especially for sparse entities. We have also showed the efficacy of using embedding confidence as a metric for mining quality rules, using that as a pruning strategy. In all, we have developed a flexible framework which can be applied to any embedding method and rule mining approach. This works toward a broader goal of unifying symbolic and neural based methods. So thanks for listening, and I hope you enjoyed viewing this presentation. I had a fun time doing this for the Purple Retreat seminar, and thanks again.